Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So, I grew up eating a lot of pasta, like I think a lot of Italian Americans did. It's like a pretty common American dish. And I grew up always
Tasty.
hearing it's tasty, right? But I grew up always hearing like you have to salt the water. And I don't honestly remember what my parents did. Like, was it a lot? Was it a little? I don't know. But I did hear later in life that you are supposed to salt to taste. And then later than that, I heard someone say, till it tastes like the ocean. And that seems pretty extreme because I've had a lot of pasta and I don't ever remember feeling like, this was cooked in seawater. So why add salt to the water when you're making pasta? When, why, what is it actually supposed to be doing? Is this all a placebo and we're just living a lie? Like, what is actually happening?
Well, darn it, Lions, I am a chemist, not a pasta physicist, but a pastafarian. But with my very limited knowledge and very limited expertise, I will attempt to opine to this. So the first thing because part of the reason why I felt like this would be a good topic is because there's a myth that I was like, I am very confident that this is a myth. That you hear a lot. It's like, why do you add salt to the water? And a lot of times it's like, well, it increases the boiling point, so it cooks faster, right?
Right, which is, I mean, salt water does have a higher boiling point than fresh water, right?
It does.
And when I say salt water, I mean like seawater compared to like rainwater.
Yes, exactly. Like saline water, not, like water with a little bit of salt in it. Yes, it does. It does. But the thing is that like, that's one of those things that when you say it out loud, right, it like makes sense. But then when you spend any amount of time thinking about it, it starts to break down. It's like in Star Trek when, they're like the moon's gravitational field obscured our warp signature. They did not detect us. And then you're like, yeah, that makes sense. Wait. The moon, like the thing that causes tides. So let's start this before we kind of get into why we actually do it, and let's debunk that myth off the top, right? So, does it raise the boiling point to add salt to the water? Yes. There is actually a cool little equation that tells you how much the temperature of the boiling point will increase depending on how much salt that you add, right? And actually, not only does it raise the boiling point when you add salts to water, do you know what else it does to water?
Lower the freezing point?
It does do that. Very nicely done. 10 points to Gryffindor. Or whichever one you are. So yeah, and do you know why it does that stuff?
No, actually. It disrupts no, I got nothing.
So it's interesting because it actually does both of those things for different reasons, right? So when you think of water, like what does the water molecule look like?
I mean like an H and two O's.
Yeah, but more importantly is that they're bent. It's not linear, right? It's
yes.
like an H.
You've got the O and then the two hydrogens, right?
Yeah, like out to the side. It looks like a little caret, like the shift 6
it's like a chevron
on a keyboard.
Yeah.
Yep. And so now here's another question.
I can't believe we got through that without just saying triangle. It looks like a triangle.
It does look like a triangle, right? Because there's no bond on the bottom.
That's
so
right. It looks like most of a triangle.
Yeah, it looks like 2/3 of a triangle. If I had to put a fine point on it. So now here's a question that will use the amount of knowledge that you've accumulated over the years of our friendship. What type of bond is a water molecule doing?
Ooh. Let's see. There's what? Covalent.
Yep.
Ionic.
Yeah.
And then I feel like the last time you asked me this, I was also frustrated that I couldn't remember the other one because it's like got a stupid name.
It does. And actually, to be fair, like there's those three. And then there's like even other ones where it's just
certainly.
like there's.
Yeah.
Yeah.
The high school version is never the true science.
Yeah. And then there's also like hydrogen bonding and metallic bonding and organoligand bonding. And like
hydrogen bonding is the one I was thinking of.
Yeah, that's the one I don't like. And that's unfortunate because it's going to come up a lot in this discussion.
Maybe that'll help me remember it.
Yeah, right. So which one is water?
Oh, I don't know. I just wanted to see if I could get the list. I would
Well, it's
say,
one of the two you mentioned. So
Okay.
you got a 50-50 shot.
Okay, I'm going to say then covalent.
Well done. I mean, and clearly by the look on your face, you were very confident in that answer.
High degree of confidence, yeah.
So it's covalently bonded. But the interesting thing is that it's not so covalent bonding is when they share electrons, and ionic bonding is when they straight up give up electrons, right? You know, ionic bonding is the there will be blood, you know, bonding, right? You know, so I say that to say though that not all covalent bonding though is equal, right? So the oxygen is this big electronegative electron hog. It loves its some electrons. And the hydrogens are, man, they're just happy to be part of the team. So they're more than happy to like kind of give up their sharing. So what that means is that unlike with ionic bonding, where one of the atoms has a no kidding positive charge and the other one has a no kidding negative charge, they're covalently bonding. They're sharing, but the oxygen's got a slight negative charge and the hydrogens have a slight positive charge because the oxygen's like, hey, man, I'm in this, but I get 80% of the food. And the hydrogens are like, man, I just want food. So, you know.
Okay, so two things. One is that bonding is covalent bonding related to why like water kind of functions the way it does as a liquid, because it's like, oh, it's just kind of sloshing around.
More specifically, because it's a polar ionic, or it's a polar covalent bond. So the reason why it behaves the way that it does and like oils behave completely differently is because of that polarity. So like water's surface tension is literally because of the is so not to interrupt what you were going to say, but it's because you've got the electronegative oxygen and the slight positive hydrogens, and so then they arrange each other in like a lattice structure, and that's what allows them to have that surface tension, because they're literally hanging on to each other through intramolecular forces. You know,
you did the activity maybe even with your own kids, but certainly when you were a kid where you like do drops onto like a penny.
Mm-hmm.
Right. Yeah.
Yep.
Surface tension. So it is such a good, I mean, that has stuck with me my whole damn life. I probably did that when I was like elementary school. The other thing is the slight electronegativity of the oxygen is that's the dipole, because then the other one's positive, right? The dipole moment.
Yep. So yeah, absolutely. Yeah, man. Yeah. Well done.
Yeah. Slowly getting there.
Yeah. So the dipole moment is when you talk about something being a polar compound, the dipole moment is the degree of that unevenness, you know? So if it has a high dipole moment like water does, then it's very uneven sharing. And if it has a low dipole moment, then it's a little uneven, but yeah, it's mostly even. It's kind of okay. So specifically what happens as you continue to lower the kinetic energy of water, right, or lower its temperature, is that the water molecules start to lose the energy to kind of like continue to move around each other. So then they start to arrange each other in that lattice shape where hydrogens point towards oxygens and oxygens are pointed towards hydrogens. And it's also why water freezes when it or expands when it freezes, is because once they start to lock into that place, they don't like to be that close to each other, right? So I say all of that to say sodium chloride, right? Any salt, right? The positive ion comes bombastically in there and goes like, hey, I want to be a part of this too. And it screws everything up, right? So water's like, hey, man, I want to make this nice little crystal lattice. And sodium's like, me too. And it's like, oh, man, we got to deal with this guy. All right. Well, you know what? We're gonna have to get even colder before we can form this lattice structure, right? And then when they're trying to get away from it, so you're pouring so much energy into it, right, that they're now trying to get away from each other. Well, the actual positive chlorine and the actual no kidding positive sodium and the actual no kidding negative chlorine can pull on the water a lot stronger, so it can keep it in the liquid phase better than just water can by itself, right?
That's interesting. I'd never really thought before about like, oh, why does this thing boil hotter than that thing? Because usually you're talking about entirely different substances, right? Like it takes more energy to boil lead than water. And it's like, oh, but those are whole ass different things. But salt water and pure water feel like those are pretty close. So the difference must be like very specific, and it's just a little bit of electromagnetism.
So interestingly, anytime when boiling point, freeze, all that, it's all intermolecular forces. Depending on how much the thing you're looking at grabs onto the other thing that it's with, that determines whether or not it's got a high boiling point and a low boiling point, So that's kind of cool.
Yeah.
So I say all of that, though.
Exact same concept. It's just easier at the macro scale to look at metal and be like, well, metal has a higher boiling point than water.
Yeah.
And it's like, no, but it's for the same reason. It's just that it's a different material. Salt water is a different material than fresh water.
Yep, exactly. Yeah, it's a composite material. But yeah, so there's this, so with all that said, now that we've created the universe, right? In order to, so I said, like, okay, I used this equation and I said, let's just go. I just threw in some easy numbers to make the math easy. And in order to get a 1 degree Celsius increase in boiling point, right, means that your saline content would have to be 58,000 parts per million, or roughly 1/5 of a cup of salt into 1 liter of water in order to get it to go up by 1 degree Celsius. So when people are like, you got to add salt to the water to increase the boiling point, it's like, trivially,
yeah, technically yes, but practically no.
Yeah, exactly. It's like if you're cooking something that requires such a degree of precision that it needs to boil at exactly a certain temperature, it's like, oh, okay.
That's like Bender from Futurama levels of salt.
That salt content on that dish was 10% less than a lethal dose. Oh, I shouldn't have had seconds. Which also implies that the LD50 for salt for humans and Zoidberg is the same. And given their biology, I don't think that'd be true, but that's not the point.
Well, Zoidberg survived, so he must have been thinking about the LD50 for humans, but his is higher.
Yes, yeah, but I would think that his would be lower because he's shellfish, but,
Shellfish, saltwater animal.
Yeah, that's fair. And also he's got like a whole bunch of redundant organs, apparently. Maybe he can just process the salt better.
Yeah,
Let's talk about that instead. Why are we talking That sounds like a good idea for an episode. Why can Zoidberg process more salt than Fry? So that I just wanted to debunk that off the cuff because I didn't want to deal with that. So, what is pasta?
I mean, I guess most of it is like a wheat-based starch. It's like it's like a glutinous dough.
It's a miserable pile of secrets.
Yeah, it's a miserable pile of secrets. I'm just trying to think like it's usually made from wheat. You process that into flour. You then roll that with water and salt into a dough. Yeah.
Yep.
It's a starch.
The only thing that you're missing in there is eggs are added as well.
Eggs,
so there's starch. Yes. There's starch and protein.
Yes.
But that's it. To your point, right? Is it starch and protein? So then what happens when we cook pasta? So do you know what starch is? Because we've always heard of like starches, but because of this, I looked it up, and then when I first looked at it, I was like, oh no, I think this is a thing. And then as I dived into it, I was like, oh no, it totally is, which is starch. So you mentioned it's glutinous, right? So the root word of glutinous would be
gluh.
Glucose,
I assume
right?
You mean gluten.
Yeah, gluten or glucose, right?
Yeah.
So glucose is a sugar that we can use to do fun things like make podcasts, right? It has a whole bunch of OH groups on it.
Because it's a carbohydrate.
Carbohydrate, yep. Carbo meaning carbon and hydrate meaning hydrated, like with water. Scientists aren't super creative, man.
You say that, but then every once in a while I try to make one of those logical leaps and you're like, haha, wrong.
But to be fair, most of the time I can be like, I see how you got there. That's not right, though. So what it can interestingly do is that if it's got like this carbohydrate with an OH group off of it, is it can drop one of those H's off and then connect to basically the oxygen of, not to the oxygen, but to where the oxygen is on another glucose and make a 2-glucose chain, right? And then you can keep doing that. And then if you do it 3 times, I think it's sucrose, right? But if you do it a lot, like a lot, you create starch, which you know what that means starch is?
It's a polymer.
It's a polymer. And I swear I did not know that when I started down this road, because we've been doing a lot of polymer stuff recently. And when I found out the starch was a polymer, I'm like, well, I mean, I'm in it now. And what drew my attention to it, because a lot of so when they normally denote polymers is they say like they give you the root molecule and then they just put it in parentheses with like a little N. And I saw that and I was like, huh, that makes it look like a polymer. And then I kept digging and I was like, oh no, all of these electron microscope images, they look exactly like the polymers I've been studying. It's just a straight up polymer, right? So that's kind of a bummer, right? In the sense that like, apparently polymers are everywhere, right? But when you start to cook the pasta, what happens is so the starch has formed this like big polymeric, like, organized structure, right? And so as you cook it, what happens is the water goes like, hey man, I want to get in on this. Let me get in on this. And the starch says, look, man, I get that you want to be like cool and you've got all this kinetic energy you're bringing to my doorstep because you want to be a part of this cool thing. But I'm telling you, man, this is going to work out poorly because if you come in with your OH group, I've got all these really nice curated, like oxygen bonds and you're going to wreck them. And it's like, nah, man. I know that that's happened before. I wasn't cool at the last house party, but this house party is going to be different. And it's never different. It's always the exact same thing. Water comes rocketing in and it breaks apart the sucrose, which because it was all knitted together in a way that made sense when it was physically bonded, once it starts to break apart, the sucrose actually blows apart, right? And then, yeah. And so then the water goes, woo, time to really party. And it goes shooting into the structure of the noodle, basically, right? So water attacks that bond. And then when it goes, kind of flowing into that, while all of that is happening, the proteins are being heated. And you may know this because this is a word that gets thrown around a lot. What happens when we heat proteins?
The word that comes to mind is it denatures them.
Yeah, exactly. Yep. The protein denatures. So proteins have a very specific structure, and the reason why is because of those intermolecular forces we were discussing, right? But the thing is that proteins are so big they can have intermolecular forces with themselves, because
right, because they're like folded in on themselves, all weird.
Exactly, they're all folded in weird because there are parts of them that like other parts of them, but are separated by parts that they don't like. So the parts that like each other knit together, and then the part that they don't like just kind of hangs out to the side, right? But when you add enough heat to that situation, it's like, oh, I've got enough heat. Things are going to be great forever. I don't need to hang out with this buddy system anymore. Look at all of this kinetic energy I have. Things will be great forever. And thus they denature, and then they become softer, right? Because they stop being all knit together, right? But while all of that is happening, while the proteins are denaturing, and more importantly, the starch is blowing apart and the water comes rushing in, what the water brings with it is anything that the water's in, which is salt, right? So it's literally, in this case, to go flowing into the pasta. So that way the salt actually penetrates into the pasta. So that way it's not just laying on top of it. It is actually suffused into or absorbed into the pasta itself, so that way the pasta tastes good, if that kind of makes sense, and so the starch actually starts to absorb water quickly at 180 degrees Fahrenheit, so not at boiling.
No, is that enough that you would start to see like the kind of like bubbles and the rumble, but not like a rolling boil?
I think so. I'm not sure exactly how that works. That'd be a good episode. At what temperature does water start to simmer and then boil and then what have you? But basically is that once you hit 180 degrees Fahrenheit, you don't need it to be any hotter. If you cooked pasta at 180 degrees Fahrenheit, you'd be fine, which is why it's even more ridiculous why they're like, I want it to boil hotter. It's like, you do not need that. The entire objective is just to get the sodium and chloride, the sodium chloride, to suffuse the pasta, to actually penetrate into the pasta, and which it can only do when the starches are blowing apart like firecrackers on the 4th of July. And that's why we do it.
Just to see if I remember this correctly, you just said sodium, and then you corrected yourself to sodium chloride, and I believe sodium is explosive in water. Is that right? Yeah.
Sodium. Yep.
So it's really critical that this is sodium chloride and not just pure sodium.
I'm just because the other thing too is that like co-sign everything you said. You would never confuse those two things because sodium chloride is like a white crystal and sodium is metal, like in its
right.
it would be a hunk of metal. So I'm just picturing like somebody being like, oh, hey, I'm going to add some sodium to the pasta. And you're like, okay. And you see them like walking over with like a brick of metal and like, oh, and you're like,
an
no,
idiot.
Don't.
No, we talked about this. So I have to ask, in the course of you firing all of this off the cuff and not in any pre-research you did you come across a recommendation or even like an estimate for like what would be the right amount of salt to water? Because it's not a fifth of a cup to salt per liter of water.
No, actually, I think that of the ones you kind of said it is very much so a taste thing, right? So the more salt that you add, the more it's going to, the more salt will penetrate the pasta, and the saltier the pasta will be. One of the interesting things when I was discussing this with my wife was she said like, well, I don't like doing that because I don't think it makes the pasta salty enough, and I want to add salt to it, but I don't want to add too much salt to the pasta. And so the thing to remember is that when you put salt in the water, not 100% of that salt is making its way into the pasta, So like you can very liberally add salt to the water and then still salt your pasta, and you're not going to be like, oh my God, this is so much salt. What am I going to do? But that being said, is that it is very much so the salt to taste would be the one that I would recommend. Where if you're like, hey, you know what, and the best way to do that would be like you salt it, and then like once it kind of gets when you're tasting it to see like, hey, is this the right consistency? If the pasta tastes good on its own, then that was the correct amount of salt, So, but that is very subjective, So, some people like more, some people like less, but I think I would probably cut it at a fifth of a cup.
Yeah, this reminds me of a bunch of baking chemistry related questions I want to ask you.